Today we're going to start our chapter on chemical quantities, and this is chapter 10. Well, we just finished up with chemical equations and we balanced equations. We've been writing chemical formulas. Back in Unit 2, we learned about how to deal with significant figures and calculations. And so today I want to introduce you to a unit that we see in chemistry, and it's called the mole. And it's very, very important in our study of chemical quantities. So the mole, we abbreviate this unit MOL. It's a pretty short word anyway, so they drop a whole E off of it, if you will. But the abbreviation for mole is MOL. That would be the unit you would give. Now, I'm sure y'all are familiar with lots of types of moles. You see the little mole up here that burrows under the ground. We might have a mole on your body. Well, this is another meaning of the word mole, and it's actually a unit of measure. This is the SI unit for the amount of our substance. So our substances, remember, can be elements or compounds. The SI unit for the amount of our substance is called the mole. Now, the mole is equal to a number that we know as Avogadro's number. Now, I have shortened this number here. It's in the book, you will see it 6.0226 times 10 to the 23rd. But if you think about in terms of the mole, we're talking about elements. We're talking about compounds, very, very tiny, almost submicroscopic, if you will, particles that we can't really see. So when we're talking about having a whole mole of salt, for example, or a whole mole of carbon, that's going to be a whole lot of particles. So 1 mole of any substance is equal to 6 times 10 to the 23rd of our representative particles. Now, representative particles, we will abbreviate RP. So what exactly are the representative particles? Well, it depends on what type of substance you're dealing with. If you're talking about an element, you will call it an atom. So atoms go with elements. So like carbon, you would describe that as the representative particle for carbon would be called an atom. For molecule, that is referring to molecular compounds. So when you have a nonmetal and a nonmetal like carbon dioxide, that's a molecular compound, so you would refer to that as molecules. And when you say formula units, this is the representative particle for an ionic compound. So like table salt, sodium chloride, when you have a metal and a nonmetal. So 1 mole of any substance is equal to 6 times 10 to the 23rd representative particles. Now this is kind of similar to like if we were to use the term 1 dozen. If I said, hey, go buy me a dozen donuts, 1 dozen donuts, we all know is 12 donuts. And unless, of course, it's a baker's dozen, then it would be 13 because 1 is for the baker to try, obviously. But nonetheless, 1 mole is very similar to that in that 1 mole of donuts, if you will, would be 6 times 10 to the 23rd donuts. Well, here we're talking about tiny, tiny, tiny particles. So we need a really big number of them to make a mole. 1 mole is equal to 6 times 10 to the 23rd. Atoms, molecules, or formula units. Avogadro's number is a conversion factor that we use oftentimes to convert. So if you wanted to write it as a conversion factor, Avogadro's number is 6.02 times 10 to the 23rd molecules, atoms, or formula units. We can say representative particles equals to 1 mole. We use this oftentimes as a conversion factor. So 1 mole of any substance will always contain 6 times 10 to the 23rd representative particles of that substance. So here is just a diagram, if you will, that tries to explain the fact that if you have atomic nitrogen, we call those atoms. These are the representative particles. So here's what an atom would look like. When you have N2, that's diatomic nitrogen, so that's called a molecule because there's more than 1 element there. Also, molecular compound water. We're not really going to be seeing ions at this point, but so we can kind of ignore that. Formula units is calcium fluoride. Notice he's an ionic compound. So when we're talking about representative particles, it's relative to what kind of formula you're looking at. But don't confuse it. Atoms, molecules, formula units, they're just very specific to the representative particles for a given substance. So one of the calculations we want to be able to do, this is a calculation that is extremely important, is how to calculate the molar mass. Now sometimes this is also called molecular weight. Okay, so molar mass, MM, this is how sometimes I'll abbreviate that. Molecular weight, MW, you see those? Molar mass, molecular weight, they're used interchangeably. The unit of molar mass is expressed as the number of grams of the substance per 1 mole. Now we'll need our periodic tables to calculate this. The definition of molar mass is it's the mass in grams of 1 mole of an element or compound. The mass in grams of 1 mole of an element or compound. Every element on the periodic table is the mass on there that you see, the atomic mass, is for 1 mole of that substance. If you had 1 mole of it, that would be the mass that you would need to have 1 mole of that particular element from the periodic table. And we can use molar mass as a conversion factor as well. Now, just for our purposes, we're going to round our molar masses to 2 decimal places. That is just so that we all of us in class always do it the same way. And that gives us enough significant figures to get good solid answers as well. So 2 decimal places or to the hundredths place when we calculate these, and you'll see that in a second. So the molar mass is the atomic mass of the element or compound per 1 mole of the element or compound. So let's practice here. I'm going to start off with a very simple one, S8. So when you're showing your work, and remember always show your work, you're going to break it down. This is just sulfur, but there's 8 of them. Notice the subscript 8, so you're going to say 8 times. Now go to your periodic table and find sulfur. Sulfur's atomic mass from the periodic table. We're going to round it immediately to 2 decimal places when we write it down, 32.07. So 8 times 32.07 will give us our molar mass, so 32.07 times 8. Make sure you got your calculators handy here. That's going to give us 256.56 for our answer. 2 decimal places, remember, we're rounding to the hundredths place. And the unit for molar mass is grams per mole. All right, example 2. Here we have a compound, copper 1 chloride. So break the formula down into its elements, copper and chlorine. And now notice there's 1 copper and 1 chlorine. So I'm just going to keep this consistent. So 1 times copper, find copper on the periodic table. And if you look on the periodic table, his atomic mass is 63.55. And for chlorine, there's 1 chlorine in the formula. So look to your periodic table, and if you look at him, his atomic mass is 35.45. Now you're going to bring that over. Now we're just going to add it up. This is going to be his molar mass. You're going to now take 63.55 and add 35.45 to that. And that's going to give you 99.00. Remember, when you add and subtract, you go with least decimal places. We have 2 decimal places here. We're doing that on purpose for molar mass. And the unit is grams per mole. Remember to always box your answer in for your final answers here, so there's no question. Let's look at the third one, aluminum oxide. Now here we have some subscripts. We're going to break it down. Aluminum and oxygen. Take your compound and break them down. This formula shows me that there's 2 aluminums in it and there's 3 oxygens in it. So as you're writing all this out, 2 aluminums, go to your periodic table. The atomic mass of that is 26.98 for aluminum. For oxygen, 16.00. Now again, I want to point out that we are purposely rounding these always to 2 decimal places. So we're going to say 2 times 26.98. And that's going to give me 53.96. And then we have 3 times 16.00. And that's going to give you 48.00. So now we're going to add these together. This is going to give us our molar mass. So 48.00 plus 53.96. And that's going to give us for our final answer 100.